Welcome students. It is an introductory class of Boolean algebra. Definition. What is Boolean algebra? A non-empty set B on which two binary operations plus addition and dot, which is multiplication, and one unary operation. That means complementation. No complementation. Complementation. Are defined. Is said to be a Boolean algebra if the following postulates or actions, whatever may you call, given by E.V. Huntington. So what are they? Number one is plus and dot are commutative. Number two is this is the number two, 1a. A plus b is equal to b plus a, and a dot b is equal to b dot a. You all know what is commutativity. Number two is plus and dot are distributive on each other. That means a dot b plus c is equal to a dot c plus b dot c, and a plus b dot c is equal to a plus b dot a plus c. So a dot b plus c is equal to a dot b plus a dot c, and a plus b dot c is equal to a plus b dot A plus C. Okay. Number 3 is there exists in B distinct elements 0 and I which are identity elements with respect to addition and multiplication, okay, respectively. Okay, so that is a dot I is equal to I and a dot a plus 0 is equal to a. Okay, the number 4 is for all a in B the operation, okay, which is called the unary operation, okay, or the complementation, the operation this is the unary, satisfies a plus a dot is equal to I and a dot a dash is equal to 0. Okay, the Boolean algebra the Boolean algebra is denoted by b plus dot, okay, or only b. Sometimes we will write b instead of this 4 tuples, okay. So a non-empty set B whose elements are satisfying these 4 actions are making a Boolean algebra on B, okay. Similar concepts with ring, field, group, etc, etc, okay. Now one theorem is in a Boolean algebra the element 0 and I are unique, okay. Proof. To prove uniqueness of a certain element, we have to assume that there are 2 elements, okay, that we have to assume that there are 2 zeros, okay, 2 zeros which are satisfying the property 0 plus a is equal to a for all a belongs to b. Okay, and then we will show that zeros and these two zeros are actually equal. Okay, proof. Let us consider there are two zeros. Okay, two zeros, so 0 and 0 dash. So by the property of 0 and 0 dash, so we have 0 plus a is equal to a, and 0 dash plus a is equal to a for all a belongs to b. Fine. Now since 0 no by now 0 plus 0 dash is equal to 0. Okay, by the property of 0, by the property of, see, 0 dash returns 0. Okay, so by the property of 0 dash and 0 plus 0 dash is equal to 0 dash by the property of 0. Okay, so here we have used the property of 0 and here we have used the property of 0 dash, but these sums are equal. Okay, by the definition of this plus, so 0 plus 0 dash is equal to 0 plus 0 dash. Sum of two elements are never be unequal. Okay, so we have 0 is equal to 0 dash, and hence we have proved that 0 is unique, and by similar argument we can prove that the identity I with respect to the multiplication is also unique. Okay, example 1 is, let x be a non-empty set. Okay, Px is the set of all subsets of x, sets of x. Okay, so this Px is making a Boolean algebra with respect to union, intersection and the complementation of sets. Okay, which is a Boolean algebra with respect to union, intersection and complementations of sets. That means here plus is our union, dot is our intersection, and the complementation is complementation. Okay, now principle of duality. Principle of let us assume the conditions satisfied by the Boolean algebra okay. That means each of the conditions 1 to 4 contains two parts, one of which can be derived from the other by an interchange of the operation plus and dot and interchange of the identity elements 0 and I. Okay, so I am writing this. Each of the conditions from 1 to 4 contains two parts. Okay, one of which can be derived from the other by an interchange of the operations of the operations plus and dot and an interchange of the identity element elements 0 and I. Okay, the operations plus and dot and also the elements 0 and I are said to be dual of each other. Okay, dual of each other. Okay, so what I wrote I will prove. Okay, so just go through the lines and I will prove what the lines are saying. Okay, in a Boolean algebra, complement of I is equal to 0. Okay, so this is called the duality. Okay? The dual of I is 0. So I dash is equal to I dash into I. Now since dot is commutative, so I dot I dash. Okay, now I dot I dash means 0 by the property 4. Okay, and similarly we have proved just I dash equal to 0. We can prove that we can prove that 0 dash is equal to I. Okay, so 0 dash proof. Okay, zero dash is equal to 0 plus 0 dash. Okay, so since plus is commutative, that means 0 plus 0, 0 dash plus 0, and this equals to I. Okay, so here observe that the property and its dual, this is a property and it is a dual of this property. Okay, are proved in a few similar steps, the dual operations being performed in corresponding steps. Okay, so this is our property and this is our dual of the property. Okay, and in view of the principle of duality, we need only to prove one part of each statement or each theorem in a Boolean algebra. Okay, so that means if we are to prove that suppose we have to prove a plus a is equal to a for all a belongs to b. Okay, and a dot a is equals to a for all a belongs to b, then we have to just prove one property. Suppose we will prove this property. Okay, proof, theorem, proof. Suppose we will prove this. Okay, and by duality we will say that this is true. See, consider this a plus a. Okay, now this means a plus a dot I. Okay, and since dot is distributive over class, so a dot I plus a dot I. Okay, but no, this step is not useful. This step is not useful to us. So this is now I is equal to this. Okay, and now we are applying the reverse distributive property. Okay, that means it will give a plus a dot a dash. Okay, now if we apply the distributive of distributive property plus over dot, then it gives this line. Okay, now what is a dot a dash? A dot a dash means 0. Okay, you can imagine this dot as intersection and the elements A as set. Okay, so intersection of a set and its complement is always give us null set. Okay, so you can think you can think 0 as a null set and I as a universal set. Okay, so our task is very easy. Okay, so it will help to think the proofs. Okay, so this will A. Okay, and uh, the duality principle says that this property is completely derived from this. Okay, so by duality of one, we have B dot A is equal to A. Okay, so as I said that plus and dot can be interchanged. Okay, similar as 0 and ring. So this is the interesting thing on duality. So I will give the formal definition of duality. That means a property, formal definition of duality, a property P of the Boolean algebra B that can be deduced from the conditions 1 to 4 has its complements. Okay, sorry, no, not complements, counterparts P dash, which can be obtained by an interchange of plus and dot and an interchange of 0 and I. Okay, so P is called the dual of P. Okay, P is called the dual of P. So by duality, we will prove all the properties, and so if we are given a property in class, and then by duality, by principle of duality, we can prove the property in dot. Okay. So there are some theorems whose proofs are omitted. Okay, just I am writing theorem in a Boolean algebra B. Okay, a plus I is equal to I, and a dot 0 is equal to 0 for all a belong to P. Okay. Proof is okay. So we will prove this property, and by duality we will say that this is true. Okay. This you know, this is called absorption. Okay. In set theory, in poset, the properties are very similar. Okay. And this, that means the complement of complement A is equal to actually A. All A belongs to B. Okay. And in Boolean algebra, De Morgan's law will hold. Okay. Is equal to, and so we will prove the De Morgan's law, this part, and by duality of principle we can conclude that this is also true. Okay. But I am not going into the proofs. Okay. And the last, the class and dots are associatives. Okay. And so these are the very important properties of Boolean algebra. Okay. Now we will move into some other definitions. Definition. A ring R plus dot, okay, with unity is said to be a Boolean ring. If a square, that means a dot a, is equal to a for all A belongs to B. Okay, so we are given a ring with unity. If in that ring A square is equal to A holds for all A belongs to B, then that ring is called a Boolean ring. Okay, and it is quite interesting that theorem, let R plus dot be a Boolean ring. Okay, Boolean ring. See, when we are defining the Boolean ring, don't be confused that R is already a Boolean algebra. Okay, by this theorem we can construct a Boolean algebra on a Boolean ring. Okay, so let R comma class comma dot is be a Boolean ring. Okay, now if we define binary operations. Okay, binary operations and unary operation on R. Okay, by A join B is defined by A plus B plus A dot B. Observe carefully that we are making new binary operations with the help of the old plus and dot. Okay, the old binary operations. So A join B is defined by A plus B plus A dot B. These plus and dots are plus and dots of our Boolean ring. Okay, or rather the ring, the given ring. Okay, A meet B is equal to A dot B. Okay, and A complement is equal to I plus A. So this is our identity, our unity in the ring, and this is our element of ring, and this is our the old plus. Okay, that means the binary operation on our ring. Okay, so then R forms a Boolean algebra with respect to the newly defined operations. Okay, so this is a Boolean algebra. Okay, so anytime if we are given a Boolean ring, then if we define these operations by such that if we define the new operations, okay, by the help of the old operations such that then all time we will get a Boolean algebra over R. Okay, with respect to the newly defined signs, newly defined operations. Okay, so this is all about our Boolean algebra. Okay, so this is very basic and introductory class. So now I am stopping my class here. Okay.